Hi everyone, my name is Dennis Gravert and welcome. We're going to start talking about organic chemistry. So if you have access to Canvas, you might want to download something called the key concepts. These are incomplete lecture notes. I'll show you what they look like. Here we go. So these are guidelines to how we're going to just whole class here. So I got these notes here. We'll go through them step by step and make notes on the page here. And if you have your own copy, then go ahead and mark them up as well. You can mark them directly up on Microsoft Word, or you can print them out, use a pen and pencil, whatever you want to do. Or if you got a photographic memory, just watch the whole thing, huh? Wouldn't that be nice? Okay, let's go ahead and get started. So, key concepts for Unit 1, Part 1. And it's actually going to be split into two videos. So let's cover most of these items in the first pass here. Let's start with a definition of organic chemistry. It's simply the study of carbon-based molecules. You may have heard the expression that we are carbon-based life forms, and what that means is that many of the molecules that make us up, molecules that are responsible for life, contain carbon. You can think about DNA, proteins, and carbohydrates, and lipids, and all those important biological molecules. If you look at their chemical structures, you will find a lot of carbon. Okay, a lot of carbon in these big molecules, that's going to be difficult to draw or tedious to draw. Sure, small molecules like over here in the bottom right corner of the screen, there's only 2 carbon atoms and there's 6 hydrogens, 1 oxygen. That ain't so bad to draw out. But when the molecules get a little bit larger, and that's typical of biological molecules, that's a lot of C's and H's to have to keep on drawing. So there is a shortcut. It's called skeletal drawings. And we use them a lot in organic chemistry because it's the study of carbon. So what are we going to do with the skeletal drawing? Well, here's a few features we'll go over, and then I'll talk about how to convert between the different ways of drawing molecules. Looking at the skeletal structure, what's something important about it? Well, the first thing I notice is, hey, there's no C's in here. Every time there's a bond that doesn't have an element specified, we're going to assume it's a carbon atom. And so this line happens to be, in this case, a single bond. This double line is a double bond. And at the end of the right-hand side of the bond is an oxygen. Okay. Over here, there's no element specified. It must be carbon. There's another single bond connecting nitrogen to carbon, and so on. You might remember that molecules are three-dimensional. And I don't know if you've seen this before, but you can use a wedge bond to sort of illustrate that the bond is coming out of the page, out of the computer screen towards us. And then this dashed bond is going away. We'll go over that in a later video, but I just wanted to explain it right here because it's present. Let's see. Hydrogen. So there's going to be a lot of hydrogen atoms in our molecules. And if we're leaving out the C's, we're also going to start leaving out some H's. The exception to that is anytime a hydrogen is connected to an element that's not carbon, in which case we're going to be obligated to draw in that H. Okay, those are some basic traits of a skeletal drawing. Let's see how we can convert from something you might be more familiar with, these structural formulas where we show all the elements, C, O, and H, and all the bonds. Okay, so we're going to start with this molecule, which happens to be ethanol, the alcohol of beer and wine. And I got a little step-by-step procedure how to convert this drawing into a skeletal drawing. One, get rid of all the C's. So let's switch over to the eraser. And maybe on the second drawing over here, let's delete those C's. Done. That's step one. Step two, let's take out the H's when they're attached to carbon. Otherwise, you got to keep them. Okay, scroll down a little bit more. And let's repeat what we did before. We got to take out the C. That was step one. Now take out the H's. And you know what? Before I erase the H, let me take a look at rule number 3. Here's step number 3. You want to keep the lines, the chemical bonds, unless they're bonds of hydrogen. So keep lines except bonds to H's. Okay, so I'm about ready to erase this H. Hey, this dashed line is a chemical bond to that hydrogen, so we're supposed to lose it. So out it goes. Here's an H with a wedge bond. The hydrogen's coming towards us. Well, take away the H, step 2, and the bond to the hydrogen. That's step 3. H with the bond, go away. H with the bond, see you later. H with a chemical bond is gone. This H is not connected to a C. So we keep the H. That's step 2, so don't erase this H. However, we still erase the bond to it. Okay, that looks a little funny. So let's clean it up a little bit, switch back to the pencil mode, and we'll just redraw this. I got this horizontal line here, and then I got this bond that's up and to the right, and it ends with an O. And then the hydrogen, well, looking up here, was attached to the oxygen. And there we go. There's our skeletal drawing, whoops, skeletal drawing for ethanol. Not too bad. Let's go the other direction. Well, if we start with the skeletal drawing, and we have to convert it to the full structural drawing. The full structural drawing is the one where we do see C's, where we do see carbon atoms and hydrogen atoms. So how do we go in the other direction? Well, got a 2-step procedure for you. Step 1, realize that every line, bend, or intersection of lines. Now, what's a line? That's a chemical bond. So anytime you have a bond, that's connecting 2 atoms together. And so the bond is going to represent a carbon atom if there's nothing specified at the end of a line, end of the line. Or if the line is bending, that's really 2 chemical bonds coming out. Or if there's a bunch of lines intersecting, that means there's several bonds. Think about this point right here. You can see that there's 4 bonds, right? Okay, to my left and up is this bond here, but there's a pair of lines there. That's a double bond. There's a double bond there. And this dot right here is a carbon atom because there's no element specified. On the other side of the double bond, there's no element specified. That must be another carbon. And then this vertical bond dropping down, well, that's a single bond that connects this carbon to oxygen. And then, do I have a step here? Not really, should have a step. Why don't we expand this? The O and H are connected by a single bond. And then we're zigzagging here. So starting with the dot, which is this carbon, we're going to go up and to the right. And then we bend. Another line going down. Wait a minute, what's happening with this bond? Well, this bend is a carbon. We can do a little better than that, can't we? Hope so. That's all. There we go. Okay, and then it zigzags down, bends again. There must be a C here, and then it goes and ends with an ends with an N. It ends with a nitrogen atom. Be a little careful, right? You probably notice a gap here, And so technically the end of the line still connects to the end. There's not enough room to put a new bond between the end of this line and then to the end. Just realize that, hey, there's a line here. That's this line here. Connects something here that not specified. Well, that's carbon. And that other side of the bond connects to nitrogen. And then there's two H's connected to this nitrogen atom. There we go. That was step one. Step two, you got to remember that carbon bonds 4 times. And I had some students tell me a quick little memory aid that help us all remember how many bonds the most common elements bond. Remember HONC, a little acronym, H-O-N, well not K, but H-O-N-C. The H stands for hydrogen and halides. O stands for oxygen. The N stands for nitrogen, and the C stands for carbon. And then what position of those letters? 1, 2, 3, 4. Hydrogen's the first one. So hydrogen and halides typically only bond 1 time. Oxygen's the second letter. It bonds twice. Oxygen does. Nitrogen 3 times. Carbon comes last. It's the 4th letter in the word HONC, spelled with a C. So carbon bonds 4 times. So this carbon's nice and happy. It's got 2 lines coming to the left and up, line up and to the right. That's the 3rd bond. And to the C, there's a 4th bond pointing down. It's all done. But this carbon's not happy. It's supposed to bond 4 times. Whoops. Toggle that back. Sorry. And of course not. There we go. Okay. We're talking about this C over here with only 2 lines. It needs 4. So that takes us to step 2. Carbon bonds 4 times. So if any carbon does not have 4 bonds, those missing bonds are bonds to hydrogen. Okay, so this carbon needs 4 lines coming out. It had 2. I just added 2 more. It's got a total of 4. And you attach those bonds with H's. Now, why didn't I use a double bond? Well, the missing bonds are bonds to H. And hydrogen only bonds once. Okay, so that means all H's have to be attached by single bonds. Cool. This C had 4. This C, I only see 2 lines. Let's spread out these bonds, right? Bonds are pairs of electrons, and electrons repel. So it makes sense to spread out these bonding electrons. These 4 single bonds are spread out, got H's at the end of them. This carbon only see 2 lines. It needs 2 more for a total of 4. H's at the end of those lines. Hey, nitrogen, how you doing? It's got 1, 2, 3 bonds. That's its normal bonding pattern. It's happy. We're done. So there we go. Those expanded structural formula for that molecule. Cool. Let's see, what else can we cover in a few more minutes before we have to switch over to a second video. Zwitter ions, no, let's do that next video. Curved arrow, definitely next video. Isomers, this won't be too bad. Isomers, I'm hoping you've seen that in Gen Chem before, but if not, here you go. Isomers are simply different molecules, but they have the same chemical formula. As an example, we've got C4H10, 4 carbons, 10 hydrogens. That actually represents 2 different molecules. This is the way you could assemble these 4 carbons and 10 hydrogens. You can place all 4 carbons in a row. And wait, carbon has to bond 4 times. So then attach enough hydrogens, single bonded. So every carbon bonds those 4 number of times. But you could also have 3 carbons in a row. And then branch the 4th one out the middle. That's a different arrangement. Now attach enough hydrogens so the carbon bonds 4 times. And every carbon will be happy, meaning it's stable. But now you got a different structure. It's not a nice linear molecule. Skeletal drawing, I keep pointing at that because that's my preference, but you might be more familiar with these full structural drawings. Hey, this is a nice three-dimensional model. These three drawings all represent the same molecule that has the nickname or common name N-butane. And an isomer of it, an isomer of butane, hey, the common name is actually isobutane. That's logical. And the three-dimensional shape here, skeletal, structural. Yeah, these represent the same molecule that happens to be different than this one. They have different boiling points and different melting points. They react differently too. They're different. But they have the same chemical formula. That's so nice. That's what we're stuck with. Got honk down here, can't remember why. Oh, I do. As we add more atoms to our chemical formula, we're going to get a greater number of possible isomers. And I don't know of a way to predict how many possible isomers there are. It's mainly found by trial and error. So what you do is you got a big chemical formula, C10H25, with a nitrogen and a chlorine and maybe a couple oxygen atoms. Wow, okay, just start putting them together, bond them up, and you can predict the stable molecule as long as you follow honk. So as you link all those atoms together, just make sure you're not giving carbon 5 bonds or leaving it short with 3. This carbon bonds 4 times. Your nitrogen should have 3 bonds. Oh, one more thing I forgot to mention. I'm fine with this drawing, but is this a proper Lewis dot structure? Lewis dot structure should have 8 dots, right? The octet rule for Lewis dot structure. So right now, nitrogen sees 1 bond, 2 bond, 3 bonds. 1 bond, 1 single bond equals 2 electrons. There's only 6 electrons around nitrogen. So technically speaking, to get a good Lewis dot structure, I need a lone pair around this nitrogen. Same is true for oxygen. I only have 2 lines. 1 line equals 2 dots. There's only 4 electrons around this oxygen. Wait, octet rule, you need 8. So now there's 5 electrons, 6, 7, 8. Cool. Any lone pairs for carbon? No. 4 bonds, that's all it needs. And 1 line equals 2 dots. So this carbon has that's 1 bond, 2 electrons, 4 electrons, 6 electrons, 8. Hydrogen has a duet rule. It only needs 2 electrons. So 1 bond satisfies its valence shell. Cool. Anyways, if you have big chemical formulas, just willy-nilly start attaching them together and check honk. And if you verify we have a good Lewis dot structure, which is, it usually happens as long as you obey these bonding patterns of honk, you'll predict stable molecules. Let me check below. Am I missing anything down here? Nope. Let's go to the right. I think I got a quick review over here. We'll see how quick it is. Atomic and hybridized orbitals. Okay. So, quick review. Hopefully this will look familiar. If not, you can email me. We can meet on Zoom and discuss it in a little more detail. Okay. Organic chemistry study carbon. So let's look at carbon. The atomic orbitals, you might recall, let's see, carbon is element number 6. So it normally comes in with 6 electrons. You put 2 of them into the 1s orbital, the next 2 into the 2s, right? You're filling from the ground level, filling from the bottom up. And then the 2p, well, those 3 p orbitals have equal energy. So you put 1 electron in each one, and then we run out. There's only 6 electrons in the natural state of carbon. Okay, so then we're done. There's carbon, but we want to make molecules out of these atoms of carbon. And so we have some choices. I should say nature has some choices. What you can do is say, hey, let's take the valence electrons. everything in the outermost shell, the second shell, the 2s, the 2p. And we'll take this s, and we'll take these 3 p's, and we'll grind them up and crank out some new orbitals. 4 orbitals are going in, so 4 orbitals have to come out. And we're going to call these new scrambled up orbitals hybridized orbitals with the nickname of sp3. And that's because 1s and 3 p's went into making these 4 orbitals. So I hope you've seen sp3 hybridization before. You might have seen something that looks like this, right? The 2 p's and the s. They hybridize to make 4 orbitals that are sp3. In terms of these orbital shapes, now remember, orbitals, I kind of think of them as parking lots. Parking lots where you park the electrons, or electrons are in motion, so maybe they're like airplanes or something orbiting planets. It's their flight pattern. So if you put electrons into the p orbital here, the electron flight pattern is going to be maybe a little figure-8 dances so that it stays in the p orbital. If you put an electron in this p orbital, the flight pattern is up-down. P orbital here is in and out, so electrons are flying in and out. And if it's in the s, hey, it can go anywhere in that sphere. But you take these 4 parking lots, these 4 flight patterns, scramble them up, you get 4 new ones. And now they have different orientations. They're all angled. The original ones are at 90-degree angles. The new ones are at 109-degree angles. And what's kind of cool is if you connect all these orbitals, these parking lots for electrons, back together, it approximates a sphere. Sometimes you see sp3 orbitals drawn this way. What can you do with them? Well, you can put electrons in those parking lots and have those electrons be your bonding electrons. So you can arrange an atom, let's say it's carbon with 4 sp3 orbitals, and put a hydrogen at the end and create some methane. That's at the top here. There it is, methane, and get the arrangement of sp3. Nitrogen works well. We can create ammonia. You just have to remember that nitrogen prefers only 3 bonds, HONC, H-O-N-C, 3 bonds. And the other region for the 4th sp3 parking lot there, we need to put in 2 electrons that are not attached to anything, a lone pair. And that'll satisfy the octet rule, right? 2 electrons, 2 electrons, 2 electrons, and 2 electrons. There's 8 electrons around nitrogen. Satisfies the octet rule. Water is also sp3 hybridized, or the oxygen atom is sp3. The 4 parking lots, all the sp3s are arranged this way. It's just that 2 of those parking lots, 2 of those orbitals have lone pairs in them. The other 2 parking lots have bonding electrons, and that gives water molecules its bent shape. And the angle there is approximately 109.5. All right, that's sp3. You can do things similarly with sp2. So on sp2, grab these 3, an S, a P, and a P. So you got an S and 2 P's, but we didn't use this thing, so it's still there. We have a P orbital left over. That's what this is saying here. We have 3 sp2s and a p orbital. And if we're talking about carbon, then the p orbital might be up and down. And those sp2 orbitals, well, they're parking lots for electrons. Electrons repel, so to spread them out, they're going to have a flat triangular shape. Yeah, trigonal planar or flat triangle shape. And if we take 2 carbons that are sp2 hybridized, so here's the triangle shape, p orbital up and down, triangle shape, p orbital up and down. You're going to have the sp2 orbitals sideways overlap here. That's going to create a sigma bond. And then this p and this p can sideways overlap to make a pi bond. Now p orbitals have two lobes. So the top lobe up here, top lobe, they're going to overlap also. And I know physically this bubble of the p orbital looks really far away, but the atoms, we zoomed out. We've kind of expanded this molecule so we could see how it's constructed. The real thing, this bond angle is really short, and that brings these lobes of the p orbitals together so they can sideways overlap. And so what we get is a sigma, which you can use the Greek letter sigma, and we have a pi bond, well, you know the Greek letter for pi. And we have two bonds that make up our double bond. So you might arbitrarily say, hey, maybe this top one is the pi, or maybe it's a sigma, but one is sigma, one is pi. Why are we doing this? Well, the reason why is it's going to help us understand how molecules react. In Unit 2, we're going to see that double bonds, carbon-carbon double bonds, do a lot of reactions. And there's an interesting pattern that'll be helpful for us. So think about a reagent attacking this double bond. Maybe an acid. Let's see, what's an acid? H plus? Yeah. H pluses are acids, things that donate H plus. So we have an H plus that's going to collide with the double bond. So maybe it comes up from the bottom or comes in from the top. If it comes in from the side, it's going to bump into these H's and bounce off. It's going to react with the double bond here. But which set of electrons are going to collide first with the H plus if it comes from the bottom or comes from the top? The pi bond or the sigma bond? Well, the pi bond. The pi bond is sticking up and sticking down. The sigma is hiding in between the two regions of the pi bond. It's kind of camouflage. It's tucked away in the middle. It's the pi bond that reacts. So pi bonds of the double bond is going to be the most reactive, and it's going to change. The sigma bond is going to stay put. It's kind of protected. And that's going to be the pattern of carbon-carbon double bonds. They're going to change from a double bond to a single bond. Cool. This video is getting kind of long, so I'm just going to throw sp hybridized orbitals up here. Right. You see the pattern, I hope. We're only going to take an s and a p to make sp. Going to leave two p orbitals. We got up, down, in, out, and the up-down portions can make one pi bond. The in-out p orbitals can sideways overlap to form a second pi bond. So something like nitrogen gas, which has a triple bond between the two nitrogens. Yeah, that's one sigma, the middle one. An up-down p orbital sideways overlapping is a pi bond. The in-out p orbital sideways overlapping is a second pi bond. We have a total of 3. Alrighty, I'll see you in the next video.